Swayam Prabha. Digital India. Educated India.
Welcome to this lecture of flow through porous media. We were discussing about immiscible flow of two phases, and in this connection we had talked about relative permeability and two phase flow. And now what we are discussing at the last lecture was this Barclay-Leverett formulation, and we had particularly discussed about a porous medium which is containing only the which is containing wetting and non-wetting phase, and it was at interstitial saturation. That means wetting phase is at interstitial saturation, and so it is primarily non-wetting phase. And then we are injecting wetting phase. So, it is primarily oil, 90% oil, 10% water, and now we are injecting water from the left end. So, and we are trying to see how saturation changes within this porous medium and how what we get at the outlet. So, now we had discussed about these form of Barclay-Leverett equation. We had talked about these as this was so these gave me our conceptual understanding is something like this, that if this is the porous plug, we have as if we have saturation packets at the inlet, and these saturation packets are traveling into this medium. Some are traveling far, some are traveling this much, depending on what is the saturation value of this packet. So, this one is maybe having a saturation value of 0.4725, one is having 0.6321. So, depending on the saturation, these XSW is the distance that particular saturation SW will travel. It depends on del FW del SW value for that particular saturation. So, whatever saturation we are looking at that saturation, whatever is the del FW del SW value, this saturation packet will travel at that same rate. And how we get this del FW del SW? We said that this we have to generate a curve of FW SW, either a curve or a relation, FW as a function of SW. We need to produce a curve like this, where this is the curve. So, FW will vary from 0 to 1, and this curve we can obtain because we know what is the definition of FW. Definition of FW is equal to Kr by mu for wetting phase divided by Kr by mu for wetting plus Kr by mu for non-wetting. So, this is depending on some correlation that we put for Kr wetting and Kr non-wetting, depending on those, these we can find out how FW versus SW curve will come out. And then for any SW that we are looking at, these SW will travel by what distance given the time t. So, we have to find out what is the corresponding SW. Let us say we are looking at this SW. So, we go up there. This is the FW versus SW curve, draw a tangent there. So, this gives me the slope of this, gives me the del FW del SW, measure the slope and then put that slope here. Then you know that this particular SW will travel up to this distance. X0 is 0 at the inlet, that means all saturation packets at t equal to 0 wherever that is. So, we assume all of them are at the inlet. So, then this is 0, this del FW del SW for this given SW we can find out from the curve, that SW we find go up there, find this location, draw a tangent, find the slope, put it here. We want to know at a particular time how far this saturation front has travelled. Qt is known to us, this is Qt, and phi and A, these are known to us. So, for a given time how far this saturation bracket will travel depends on what is the slope of this FW-SW curve at that saturation, because slope is changing depending on what is the saturation, right. So, at the for that particular saturation we are talking about, this we have to find out that slope. So, we said that each saturation, so we considered when we inject water, we are injecting water at rate QT, and but we are assuming that it started with SWI, and now, so we said that there is a range possible for saturation within this porous medium. The lowest value is SWI, the highest value is 1 minus SNWR or 1 minus SOR. So, within this range, whatever saturation packets are possible, they will travel as per this equation. Okay. So, each packet we need to find out how far they travel, and based on that we have to generate the curve, how saturation changes with distance. So, now let us proceed further. So, now if we look at this expression once again, here we have dx. Dx, if we leave it here, dx would be this side. I mean, when before integration, if we break it up in differential form, it would be something like this, that dx would be equal to qt divided by phi a. Del Fw, del Sw, we can write this as Fw prime, but mind it, Fw prime does not mean del Fw del T. It is not a time derivative, it is the derivative with respect to saturation, it is del Fw del Sw. So, that we are writing it as Fw, and we write this as dt. I mean, from this equation we can write this, right. So, now this equation only this is carried forward. So, dx is equal to qt by phi a Fw prime dt. This is what we said earlier, right, that just now I mentioned. So, only thing is now you have in the denominator we have one L on the left hand side and one L on the right hand side. This is one additional. The other term dx is equal to qt divided by phi a Fw prime dt is following from the earlier expression that we put there. So, now let us see this qt by phi a, qt divided by phi a, what they are doing is, let us say we club these together, we club this part together, phi a and L. L is the length of that core. We have this core, the porous plug, and on which we are doing this exercise. So, this is the length and A is the cross sectional area. So, A into L is the over total volume and multiplied by porosity, phi into A into L. So, this gives me pore volume, right. Pore volume is what is the void volume of this core. So, that is written by capital Vp, V is capital. So, this is the void volume, okay. It is this I have a porous plug and I have a porosity, instead of that now I am talking about the void volume, and that is capital Vp. So, instead of phi into A into L we can write it as Vp, and Fw prime qt and dt they remained as it is. Left hand side is dx by L, okay. Now, you think of it, we are looking at qt dt. What does qt dt mean? Qt dt means this qt dt term, qt is the total flow rate multiplied by d. So, over dt time interval, over dt time step, qt dt is the total flow that has taken place over this dt time. So, qt is in meter cube per second, dt is some delta t, small time step. So, that is in second. So, this gives me so much of meter cube, this second and second will cancel out. So, qt dt gives me that so much of meter cube of flow injected into the system, right. qt was the total flow, okay. Total flow injected, or since it is a steady state process, so you can say that at any location, let us say in this location, I have some amount of QW flowing, some amount of QNW flowing. So, waiting phase flow rate is there, non-waiting phase flow rate is there, and there some we are calling it QT. Okay. So, QT dt is the total flow that has taken place at any location over time dt. Okay. So, now if we divide it by the void volume, what does that mean? We are writing it as dVp. I have flowed 100 meter cube of fluid at a particular location over certain time, 100 meter cube of fluid, and I know that the pore volume, the original volume was 150 sorry, not 100 meter cube, 100 milliliter. 100 milliliter I have flowed at for over a particular time over this porous medium. This porous medium, the total volume is 150 ml. Out of that, porosity is 1/3. So, when I multiply it by 1/3, it becomes 50. So, 50 into 150, sorry, 150 into 1/3 is 50. So, 50 milliliter is the void volume. So, my Vp in that case is 50, and A into L, that gives me a volume which is 150. I have arrived at Vp is 50 because we assumed phi to be equal to 1/3. So, now out of this, now this is Vp is equal to 50. Suppose I have injected 250 milliliter at some point. Let us say 250 milliliter. Let us say I am not talking about meter cube per second, we are talking about milliliter per second. So, 250 milliliter I have injected. So, 250 milliliter would be equal to 250 divided by 50, that is equal to 5 pore volumes. That is what we had, that is what we discussed before. That pore volume would be then a unit instead of milliliter. So, then what exactly we did? Whatever volume that has flowed, we divided it by Vp, right, the void volume. So, here also exactly the same thing, Qt multiplied by dt, that is the total volume that has flowed through some grid, and that divided by the Vp, which is the total void volume. This gives me dVp, that is the pore. So, dVp here you note down, dVp is volume of water injected in units of pore volume. So, dVp is volume of water injected in units of pore volume over this duration dt. Let us say if we want to qualify this, over duration dt. So, this is how. So, what do we get here? Dx divided by L is equal to Fw prime dVp, where dVp is over this time dt, I have injected some waiting phase which is water over this time dt, and whatever I have injected, if I convert it to this to pore volume. So, say I have injected 250 ml over this time dt, I am not going to express it in terms of 250 ml. Instead, I will express this as 250 divided by 50. So, I will express this as 5 pore volume. So, this instead of 5, so this 5 is same as the dVp, right. When we do the integration over dVp, when time t is finite time from 0 to some finite time, then dVp, when we do the integration, this becomes Vp, but that Vp would be always small Vp. So, mind it, in subsequent exercise we will write small Vp. This would be the pore volumes. Probably the best way to express it is, you remember, Vp pore volumes. When you see these volumes, that means I am talking about these injecting 5 pore volumes, whereas if somebody said only pore volume, no S, that means we are talking about capital Vp, which is basically the void volume. Okay. So, void volume is fixed, that is 50 ml, but pore volumes, it could be 2 pore volumes, 5 pore volumes, 6 pore volumes. If somebody says I have injected 10 pore volumes, that means that person has injected 50 into 10, that means 500 milliliter. So, this is how the arithmetic works here. So, for each value of SW, now for each value of SW we are looking at this. So, we said that suppose I, so what this expression is all about, let me clear this. What this expression says is dx by L is equal to Fw prime dVp. This is the final expression we have. So, now we here we note that at for each value of SW, let us say we pick up this value of SW. So, this value of SW we go there on this Fw versus SW curve. You can see Fw is within this limit Swi, and we should be writing it as this corresponds to SOR or SNWR, but this is actually basically this is the value here. If you put it in one scale, this is 1 minus SNWR. Okay. So, basically this is, let us say we are talking about 0.1 here. If this SOR or SNWR is also 0.1, so then this we are looking at 0.9. Okay. So, this our play of Fw is between 0.1 and 0.9, and at 0.1 Fw is equal to 0, at 0.9 Fw is equal to 1. Okay. So, that means here when the saturation reaches here, all flow that takes place, entire Qt is comprising of Qw, because Fw is equal to 1 and Fw is equal to Qw by Qt. Whereas, when it comes to the saturation is Swi, then here I can see by looking at this curve that corresponding Fw is 0. So, Fw is 0 means Qw by Qt is 0. So, that means there is no waiting phase flow. So, only phase that is flowing in this case is non-waiting phase, and in between, at any in between point you look at, so it would be flow of both phases taking place, both waiting and non-waiting phase. And what is the saturation as the flow continues this way? What would be the saturation? That a particular saturation SW will travel by a distance dx, or dx by L is the fraction of total distance. Total distance is L. Total distance is L. Out of that, a saturation packet starting from the inlet, it would travel a distance dx. That dx by L would be given by that, for that particular saturation packet, what is the Fw prime value, that means the slope of this line, and over this, I mean for this displacement to happen, you must have injected some amount of water or some amount of waiting phase from the left end of this, at the inlet, and that amount here is dVp. So, you have injected dVp. So, now you are trying to find out the saturation, how far it would travel, which saturation, some saturation you have in mind. So, simply draw that, find out Fw prime, dVp you already know, you have imposed it. You can say that this much of distance this saturation front will travel. So, dx by L would be this. Now, so what do we have here? If we now think of that upon injection of dVp pore volume, upon injection of dVp pore volume of water, we have injected dVp pore volume of water, we just now discussed. Any saturation SW, that we are talking about saturation packet, okay, saturation packet SW will progress by distance dx, where these dx, in the earlier page we had dx by L is equal to Fw prime dVp, or L we can take this to the right hand side. So, where dx, this dx amount, that movement that takes place is equal to L Fw prime dVp, and Fw prime corresponds to the slope of Fw-SW curve at given saturation. So, we are talking about a particular saturation here, and for that saturation, what is the slope of Fw-SW curve? So, we have drawn this, we have found out what is this Fw-SW curve. For this saturation we went up and found out for that saturation what is the slope of this line. Okay. So, from this we have drawn a tangent at that point on this curve and found out the slope. Now, if somebody does an integration of this dx equal to L f w prime dVp, then upon integration what they get is x is equal to L f w prime Vp, because if you do this integration on dx, then you have to do this integration on dVp. So, this would be the, so what do we get upon integration? Distance swept by saturation SW for Vp per volume of water injected. So, we are talking about dVp, now we have integrated it, now we are talking about a finite volume. So, Vp per volume of waiting phase is injected from the left end, and we are trying to find out any particular saturation, any saturation which lies within this range of SWI and 1 minus SOR or 1 minus SW SNWR. So, within this range any saturation packet, how far it will travel. So, that distance is x. So, this distance is x as far as this particular saturation is concerned. So, it will travel up to this distance x. How would you get this? This x is equal to L multiplied by Fw prime multiplied by Vp. Vp is the pore volume of water or pore volume of waiting phase injected at the left end. So, what we note here is prior to breakthrough of Barclay-Leverett front, only non-waiting phase is produced at the outlet. So, what we discussed, we briefly talked about this. This is something like this, that if you are plotting pore volume PVs of water injected, water and waiting phase synonymous, water injected. So, what does this mean? So, this is essentially Vp, right. So, this is essentially Vp, and here if we write pore volumes of oil produced, I write oil to just synonymously with non-waiting phase, oil produced, let us say. So, we said here that this will follow a straight line, because prior to breakthrough of Barclay-Leverett front, only non-waiting phase is produced at the outlet end, because this is, say, let us say this is x equal to L. So, the plug runs from, so this is the plug, so this is the plug. So, plug runs from x equal to 0 to x equal to L. So, the front has come, the Barclay-Leverett front has come up to this point. Beyond this point, the saturation is interstitial saturation, SWI. So, this SWI can never move, SWI is all trapped. So, though I am injecting Vp from this side, I am injecting pore volumes of water here, but what is moving at this location is basically oil, and what I am producing here is oil, and system is all incompressible. So, if I inject Vp amount of water, I will be producing Vp amount of oil. So, that means that this would be a 45-degree line. Whatever pore volumes of water I am injecting, the same pore volumes of oil is produced. But the moment this front reaches the end here, beyond that point, it would be producing both oil and water, because it's, let us say, beyond this point, let us say this saturation would come here and arrive. So, this saturation means here now this saturation is not SWI. So, when this saturation breaks through, so that means it is a part is oil and part of it is water. So, now, so when this saturation breaks through, then we have both water and oil producing at the outlet. So, from this point on, this will start carving, and we said that the limit here, how much is the total pore volume we can produce, is limited, because this is the total pore volumes of oil we can produce is 1 minus SOR, because we have to leave, say I have 1 pore volume of fluid in that system, out of that I have to leave SOR amount of oil in the system. Okay. So, naturally it is, I have to start with how much of pore volume of oil we had. We had to start with, we had SWI pore volume of water, because SWI is just a fraction. Suppose we are talking about out of 50 milliliter, we have 10 milliliter of water, and suppose we have out of 50 milliliter, we have 10 milliliter of water and 40 milliliter of oil, okay, and 10 milliliter is the limit. So, SWI is the pore volume of water present in the system. Okay. So, remaining 1 minus SWI was the oil present in the system, oil present in the system. 1 minus SWI was the oil present in the system, and SWI amount of water was present in the system. And when at the end, when this place is completely flooded with water, so then also we have to leave some amount of oil, and that oil is the residual oil. So, that is known as SOR. Okay. So, at that time, what would be the fraction of oil that is remaining in the system? That is SOR. So, SOR pore volume of oil, can never be produced, because that is a system dependent. So, SOR pore volume I have to leave there, and to start with I have 1 minus SW of oil present. So, out of 1 minus SW pore volumes. So, 1 minus SW pore volumes of oil was present in the system, and at the end SOR pore volumes of oil can never be produced. So, then how much pore volume of oil I have produced? Essentially I have produced, if you look at, it should be 1 minus SOR. So, SOR pore volume of oil will remain. So, 1 minus SOR is the pore volume of oil that has been produced, and we had initially we did not have 1 minus SOR. So, we had 1 minus SWI, this much of pore volume of oil was present, and out of this oil again SOR we have to leave. So, basically we have to leave SWI. So, we have a limit here, we have a limit here, and that limit we have to leave that much of SOR amount of oil, and to start with we have 1 minus SW of oil present. So, this difference, this much of pore volume of oil we can produce theoretically from this. Out of that, this linear part would be till the front reaches the outlet, and beyond that it will start carving and producing both water and oil, and asymptotically it will reach the limit when you have injected 10 or 100 pore volume of water. So, this is the overall picture. Now, the message that I am going to carry forward is this particular equation. This particular equation is going to be a key equation now. So, in the next lecture you will see that we will build on this equation to work further out, because if somebody wants to know how much of oil will be produced in this region, one has to find out how to predict this part of the curve. This part of the curve is very easy. I inject Vp, I inject whatever, I inject whatever pore volume I inject, let us say 0.2 pore volume of water I have injected, I will produce 0.2 pore volume of oil, but beyond some value it would start carving. So, this part cannot be. So, at what point this breakthrough takes place, and beyond the breakthrough how this curve changes. So, that needs to be understood. Okay. So, this is something which we will head to, and this is the equation which is going to be a key equation. You need to remember this, x equal to L F W prime V P. That is all I have for this module of the lecture. Thank you very much.